All right, so combined loading problem here. Got a rod sticking out, going like that, some sort of pipe deal. And it's got some 3D XYZ coordinate system and put dotted lines right here like this for the Y axis. The diameter of this is 2 inches all the way through. And you want to find the stress at point B. Oh, and we want to draw the different draw on an on a RVE and on a representative volume element. Okay. And so the first things first, as with anything right here, we want to find it at A, draw on a representative volume element at B. At B. So the first things first, we got to find the internal loading at location AB, which is 8 inches from right here, 12 inches from here. So it's not going to be too bad. But the challenge with these 3D problems is the is keeping everything straight. Okay, keeping everything straight. But this is all straight up from statics. So here, one is let's calculate internal loading, and this is something we've done since we first started mechanics. Right? It's so fundamental to mechanics, calculating the internal loading. And if you can't do that, you realize that your problems are going to probably suffer. But here, if I cut it right here at this 8 inches, and I'm gonna draw a little bit bigger here. So if I make this cut right here, and this is here, and then the rest of the pipe is coming out like so. Oh, I got good drawing is important here. So let me see here. Let me cut it like let me bam like this here, and then the pipe is coming out like this right here, and this is the other part of that pipe. Okay. When I add the shading, does that look like it's 3D? Not really, huh? Gosh, that's why I'm not a graphic artist or anything. But here, this is 600 pounds. This is still 800 pounds. And we have 500 going into this way. And what you want to do here is important is that, okay, I have this cut surface right here. Okay. You want to make sure you draw the coordinate system the exact same way. So here I have x, we have z was going straight up, and y is coming out right here, like that. And what you want to do also is now, instead of trying to remember like positive bending, negative bending, or anything like that, you just know that you have 3D, so you have moments and forces in about each axis. So here on the inside, internal loading wise, I have a shear force in the x. I have a moment about the x. Okay. So this is how I'm going to draw it. I have a shear force in the z and a moment about the z, like this. And then I also have here, I have a normal force in the y and a moment. That's not a very good drawing. A normal force in the y and a moment in the y. Okay? So I'm going to worry about what's in compression, tension, what direction the stresses are going based on these arrows later. Okay, I'm not going to try to I'm not going to overthink it and try to apply some positive sign convention to this and get confused. So here, I have that right here. Now I'm going to apply equilibrium about each axis and calculate. So I'm going to have in this problem here, there are 6 equilibrium equations. So we're going to go one at a time. So let's start with the x. Sum of the forces in the x equals 0. This way is positive x. So I would have Vx minus 500 pounds equals 0. That tells me Vx equals 500 pounds. Okay. Then I do sum of the moments about x equal to 0. And I have moments about x this way. And in this case, I would have mx. Let's see, what induces a moment about x? Let's see, 800 pounds is on the xy plane, so no. 500 pounds is also on the xy plane, so there's no distance that causes rotation about the x. But I have 600 pounds times an arm of 8 inches. So this distance right here was 8 inches, and this was 12 inches right here. So I have mx, and this induces a positive moment about x. Mx is 600 pounds times 8 inches equals to 0. Yeah? Everyone okay with that? That looks okay. I can live with that. Shoot, why not? Then sum of the forces in the y equals to 0. So shoot, if you're watching this video right now, you might want to fast forward this. But sum of the forces in the y equal to 0. This is plus. So you had ny plus 800 pounds equals 0. And that tells me ny equals minus 800 pounds. Okay. Then I do sum of the moments about y equal to 0. And I'd be bam, like that. And that would tell me that, do I have any moments? I would have my, and then minus 600 pounds times 12 inches equal to 0, which would be that my equals 7,200 pound inch. Okay, this is the most important part of any problem. You have to do the internal loading right. If you can't do it, can't apply equilibrium or internal loading, it's going to be tough. Okay, it's going to be tough to do anything else. So sum of the forces in the z equal to 0, upwards this time. So here I have vz plus 600 pounds equals 0, and that tells me vz is minus 600 pounds. And then sum of the moments about z equal to 0, and this is positive moments about z. So I had mz plus 800 pounds times 12 inches. And I think, plus 500 pounds times 8 inches. Yeah? Everyone okay with that for this 3D problem? This equals to 0, and then I would get mz equals some number. Minus, no, that should be positive 500. That should be positive 500 because yeah, it's going around. It's in the same direction as positive mz. Okay, and same thing with the 800. Okay, so right there, and so I don't know what that 9,600 plus 4,000, 9,600 plus 4. Is that 13,600? 13,600 negative pound inches. Okay, so so here's my internal loading, which takes a long time, but that's what you have to be able to do to solve this. Oh, I need a number for this. Mx is minus 4,800 pound inch, like this. And Vx is 500 pound inch. Okay. All right. That's pretty good. Now what? Let's see. Calculate internal loading. Now, okay, so now we're trying to find the state of stress at point B. Okay, state of stress at point B. So now we're going to look at 2 is really, actually, it's like part 2 of this problem. Part 2. So everything was just statics. Part 2, is now the mechanics, is the stress at point B. And really, all it means is going one internal load at a time and trying to figure out what stress it causes at point B. Okay, one internal load at a time, which is essentially what we have always done. Okay, so let's start with the shear Vx. Does Vx induce, if I look, so let's start, so here, I'll call this number 2. This is Vx right here, which if I look at my cross section, so I'm going to draw my cross section, I'm always going to draw my cross section as an observer for this problem today, right now. I'm going to draw my cross section as an observer standing over here looking like that. Okay, looking this way at it. So that what I would see as the observer for Vx in particular is that I would see, here's my cross section. Y would be going into the board or into the page. Y will go into the page. X will go to the right. And Z will go upwards. Okay. Is that okay? And Vx was, did we get a positive number for Vx or a negative number? What did we get? We got a positive number. So that means Vx goes like this. This is Vx. Okay. Vx is on that surface here. And point A, where we want, or point B, excuse me, this is point B right here. Okay. So the question is, does Vx induce a stress at point B? And if so, what type of stress is it? Yes and shear are the correct answers. Absolutely. So here, the shear stress at B, tau B, due to Vx is Vx(q) over IT. Okay? Right here. And at point B here, Vx, we know what Vx is. We know the direction. We can calculate I. I is equal to, looking on the inside cover or equation sheet, is pi r to the 4th over 4. Can someone calculate that for me? Okay. T is the width of that section, which in this case is the diameter, which is, what was the diameter? 2 inches. 2 inches. In fact, I don't need your help. This is pi times 1 inch to the 4th over 4. So this is pi over 4 inches to the 4th. Yay. Okay. And then Q is the first moment of area of this right here. Okay. So Q. So there's I, there's T, the width, and Q is equal to sum of A prime times Y bar prime, which is essentially the area of the half circle, pi 1 inch squared, pi r squared over 2, times the distance right here, the centroidal distance. You know, in this equation, it would be x bar prime, but it's okay. We're not modifying equations and stuff. This distance right there to the centroid of the semicircle, which is 4/3, 4 over 3 pi times 1 inch. Hey. That's 2. That's pi. And that is 2/3 inches cubed. Right? Look at how nicely that works out. Wow. Okay. And so the shear stress at B is equal to, what did we say the force was? 600? No, 500 pounds times Q, which is 2/3 inches cubed, divided by I, which is pi over 4 inches to the 4th, times the thickness at that location, 2 inches. And that gives me, I don't know what that gives me. It gives me some number in PSI. Anyone have a number? Calculator. Robot. Dude, it's been a long time. You guys have spent a lot of time with me today. I don't know, man. I feel like 2 hours is a threshold with me. You know, there's a period where I become unfunny. Although I'm sure some of you don't agree with that, right? Anyway, okay. 212 point what? 2 psi. All right. Okay, there's one down. Let's check some more, right? Yay! Okay. So here, let's go to now number 3. Let's check the moment. Let's do the moment about x, okay, which we found. And so again, I'm gonna draw that cross section. Shoot, you know, I like to do it. I like to draw the cross section because it helps me keep things in order. Here's X. Here's Y. And here is point B. And what did we get for MX? Was it positive or negative? It was negative 4,800 pound inch, which tells me that it goes this way, 4,800 pound inch. Let's see. So does this moment about X whoa, I almost messed that up. I'm confused everybody. This should be Z and Y should be into the board. Okay. Right there. It should be a Z. And so now does this moment, 4,800 pound inch, induce a stress at point B? And the answer is yes, and it is normal, just like me. Normal, right? Normal stress at B is equal to, oh, snap. We had this minus my over I equation, but I don't know if that still works here. I recommend that you just calculate the magnitude of this stress, mxz over ix, okay? And then you decide whether it's positive or negative, or compression or tension. And what does point B experience? Compression or tension here? Compression, right? Because I put my thumb in the double arrow direction and my fingers curl to pound on B right here. So here, this would just be 4,800 pound inch. The distance Z, or the distance here to this point right here, is just the radius, or d over 2, this distance, the arm. So that's just 1 inch. Yay, right? And then here, the moment of inertia, which we calculated before, is pi over 4, inches to the fourth. Okay. The moment of inertia of any axis about a circle, any axis of a circle is still the same, pi over 4. And so this is, does someone have a number for this? 6.11 KSI, 6.11 KSI. And this, I will write a little note to myself saying compression. Okay, right here. And that was pretty easy. Okay, so that's pretty good. And then now let's go to number 4, which was, let's see, what was the next one? Was it VY or VZ? Oh, we do NY. NY. So let's look at NY right here. This is a great problem. Good choice, right? We're reviewing everything. Okay, anyway, okay. So NY right here was, what did we have here? NY was, we had in this case, oh, I can't draw. So let me draw this kind of in 3D. So here is that surface again. And here is Z. Here is X. And here is the rest of that rod right there. Okay? And that observer that we were talking about earlier is right here. Okay? And so this NY was, what did we get? We got a negative number for NY, I believe. Okay? Was minus 800 pounds, which means it is going this way, 800 pounds. Okay? And this was plus y, was this way. This was the y direction. Okay, right there. And again, here is point B, right there. And on the surface of point B, what is that 800 pounds doing? Does that cause a stress on point B? Yes. And what type of stress does that cause? A normal stress, right? My favorite kind. Sigma B, due to the 800 pounds, is just N over A. And that is just going to be 800 pounds over pi r squared, pi 1 inch squared, which is 800 divided by pi psi, which is, could you give it to me in KSI, this one? Anybody? 800 divided by pi, so 0.255? Yeah, 0.255 KSI. And we're not, even we know that this right here pulling on the surface means what for that point B? Compression or tension? Tension. So we want to note that as well. Tension here. Okay? Great. Okay, let's keep going. Now we have a moment about y. So here, let me break up a page here. Because I know that the direction of my 800 pound, I know this is in tension because the direction of my 800 pounds is this way, and it's pulling on the surface, on this area right here, that surface. Can you see my cursor? Okay, all right, so right there. Okay, so that 800 pounds is causing tension. Now I want to look at the last part, 5, which is 5, not, it's not the last part, I'm sorry. It's the torsion, my, moments about y, my here. And why don't I keep this same 3D type of drawing here? So let me redraw that surface again, like that. And I know this is redundant and repetitive, but I just don't want there to be any confusion. X and then Y right here. And I really can't break this down for you any better than what we're doing right now. So here, this XY. Now this, what did we get for MY? Was it a positive number or a negative number? So we had MY is negative 7,200 pound-inch, which means that it goes this way. What did we get? Is there issue? Oh, it was positive. Okay. Oops. Let me undo that. Oh, whoa. Okay. Oh, man.